Hey guys, in this video we will be talking about differential equations. So what is a differential equation? Well, it is just an equation that contains one or more derivatives. So this is pretty broad, so let's think of a few examples here. So one we're going to talk about more and really have kind of already seen, just not in this language or context, is f prime of x is 2x. You could see something like y prime plus y double prime plus y triple prime is 0, right? So it need not just be the first derivative. We can have many derivatives. So this one, right, we're going up through the third derivative. Our first one only involves the first. You could have like y prime plus 2 y prime squared equals 6. All of these are differential equations. So since these are equations, right, they should have solutions in a perfect world. And so what is a solution to a differential equation? It's just going to be a function that satisfies that equation. So again, let's think back to an example. So f prime of x is 2x. So can you find an equation f such that this is true? Well, sure. We have talked about this with the reverse power rule, right? So if you choose f of x to be x squared, then f prime of x is 2x. And so this guy, f of x equals x squared, is a solution in this case. All right, so we got some more vocab here. So we saw, right, with f of x, or f prime of x equals 2x, that, sure, f of x equals x squared works, but we saw in class that this is not the only thing that works, right? So turns out we have infinitely many solutions, right? Anything of the form x squared plus c is going to work where c is some constant, right? Because constant doesn't change anything. We're just thinking of shifting our graph up or down. None of the slopes at any points change, so all the derivatives are the same. So this infinite family of solutions is what we would call a general solution to the differential equation. Okay, so general solution will be a family of functions that all satisfy it. And again, it's usually you're going to have some c involved, whether it's multiplicative or additive, that gives you this family. And then how do we get to like a specific one? Well, if c is specified, so, if c equals 2, for instance, we get f of x is x squared plus 2. We're picking one specific parabola, right? Our general solution gave us a whole bunch of parabolas. We get a nice little family of them. And so what are we doing here? Well, we said x squared plus 2. So it's if we go up 2 here, and so we're looking at this blue one only in this family. This is what we would call a particular solution. So basically, once you specify a value, get one function out, you get a particular solution instead of a general solution. All right, just a little bit more vocab. So the order of a differential equation is the number of derivatives involved. So what do I mean by this? Well, if we just take a look at this example we've been running with, f prime of x is 2x, then we're only talking about f prime. We're only going one deep in terms of derivatives. Only the first derivative, no second derivative, no third derivative. So this would be called a first order. Whereas I have that other example, right, where I said y prime plus y double prime plus y triple prime is 0. This would be third order because of the triple prime guy showing up, right? And so you're basically looking at the highest derivative you're taking. So this is order. Most of the things, not necessarily all, but most will be first order for what we care about. All right, so here is your first exercise for Edfinity on the class prep. Okay, so I want you to take a look at these 4 different equations and find which of the following is not a differential equation. So it doesn't satisfy that definition. Okay. All right, so let's work through an example here. So let's just see like what happens with the general solution, particular solution, and whatnot. So let's just say y prime is 4x plus 6. Okay, so we've got a nice little line. This is a differential equation, right? We've got our derivative there. So what is a general solution? So how do we find such a thing? So we know how to do the reverse power rule on this stuff, right? So for 4x, if we're looking for a y that's going to satisfy this, okay, first part should have derivative 4x. Well, I'm going to raise my power by 1. I've got an x squared. And, I know basically 2x goes to x squared. And then I've got an extra 2 left out here, right? And we can see if we took the derivative, we would get 2 times 2 is 4. Reduce the power by 1, we get 4x. We're good. To get to 6, what has derivative 6? Well, that's a constant rate of change, right? So this should just be a line. And again, reverse power rule tells us, okay, x to the 0 becomes x to the 1. And we divide by 1, which does nothing. So we get 6x. Well, this is just one function, right? And what are we allowed to do? Well, we can, again, add any constant. So this is our general solution. We get 2x squared plus 6x plus c. So how might one come up with a particular solution? Well, this comes from what are called initial value problems. Okay? So in the real world, you're often talking about, you have some rate of change, but then, maybe you are specifying a starting point, right? So maybe this y prime describes my motion over a period of time. And let's just say I started at, I was, say, 8 miles away and then, kept going at this rate 4x plus 6. So let's say at time 0, right, we're 8 miles away, and then we keep going with this y prime equals 4x plus 6 velocity, if you will. Well, what is this specifying? This is telling me, well, I know what y is, right? So I'm saying if I plug in 0 for x, that I get 8. So 8 should be equal to 2 times 0 squared plus 6 times 0 plus c. Well, 0 squared is 0, 6 times 0 is 0. So this is exactly saying that c is 8, right? And so this specifies then that y is exactly 2x squared plus 6x plus 8. And then this would be a particular solution given this initial value, right? So it's not always going to be y of 0. It could be y of 1 or y of 23. Basically, you need one point to specify a particular solution. All right, so one of the key things that we need to know is, if I have a function, is this a solution to a differential equation or the differential equation I care about, right? So again, if we see y prime equals 2x, then it's pretty easy to verify that y equals x squared is a solution, right? What do we have to do? Well, we need to just see if y satisfies this. Well, yes, if y equals x squared, then y prime is 2x. But what if I have something more challenging? All right, so we're going to look at a more complicated one here and see if we can figure out if, given this differential equation here, y prime minus ty over t, 2y over t equals t cubed, has solution this y. Okay, so here is my y, 1/2 t to the 4th plus 3/2 t squared. So the question is, does y satisfy this equation? So in order to get at that, we need to look at each of the pieces, right? So, we're saying, okay, we need to take y prime. We subtract by 2 times this function y divided by t. Do we end up with t cubed or not? So let's break it up into the pieces. First, we take y prime. So we've got y over here. It's just going to be doing the power rule twice, right? So t to the 4th, bring down the 4, times 1/2 is 2. T, reduce the power by 1 cubed, plus 2 times 3/2 is 3, and it's just t, right? Because we reduce the power to 1. So this is y prime. And then if we want to do the 2y over t part, we're going to have 2y over t. What's this equal to? Well, it's 2 times this whole y function, so 1/2 t to the 4th plus 3/2 t squared all over t. And just multiplying this out, right, the 2 cancels these denominators, so we get t to the 4th plus 3t squared over t, aka we get t cubed plus 3t. And let's see what happens. So when we do y prime minus 2y over t now, we can actually substitute in, right? So this is 2t cubed plus 3t for y prime minus what we just found for 2y over t, which is t cubed plus 3t. What happens? Well, the 3t's cancel, and one of the t cubes is gone. We get t cubed. Well, this is exactly our differential equation up there. So we plugged in this y of t, this function, and it satisfied our differential equation. Thus, yes, we get a solution here. Okay, so this is how you go about the process of deciding whether or not this is a solution. All right, and for the second problem on infinity, I want you to look at the differential equation xy prime equals 3y and figure out which of the following is a solution to this differential equation. So is x squared a solution, x cubed, 2x cubed, or both x cubed and 2x cubed? Thanks for watching.